Uh, so the first topic is data acquisition, uh, and fundamentally the exercise is not that long. The let's see, where is my exercise? There. So basically, exercise is such to make a to D converter running, have an analog sensor on it. It's a just simple simple analog temperature sensor on A to D converter. But the trick now is we do some oversampling and basically decimation. So the downsampling of that to get just those results only once or twice a second. Yes, 2 samples per second. So A to D converter is running freely, and in software you would do some decimation, meaning just running average of over the half a second time, and then just display that one into LCD. Okay, so that's the task. Couple of things before we go there. Good. So the timing of that sampling clock would be taken. You can use either the sleep timer, but now you also know how to make the timer interrupts. So the timing interrupt would be better. Although sleep timer, it might be easier. It depends. But for me, the timer interrupt is easier than sleep timer. but you can pick your favorite. Let's see. I think I should draw a couple of things on the whiteboard thing. Couple of things on the whiteboard. I have a little bit too simplified picture on the on that exercise sheet. So we have a LM35 type analog temperature sensor, which basically gives the output voltage is basically, let's see, 20 millivolts per centigrade. So 20 millivolts per centigrade degree. So 0 volts would be 0 degrees, and well, there's also a way to bias this one negative, so it actually can give negative well, Finnish temperatures. But we are in Germany. So we are okay with the this unipolar polar power supply. Okay, one warning already here. If you reverse the polarity of the power supply, this will burn. There's absolutely no protection against the wrong polarity on circuit. So every single time when I use this one on education, someone will burn the device. The last time it was me, it was myself. So take a closer look at the very careful look at the datasheet. Okay, so fundamentally, on any analog system, if we have a sensor, before making the A to D conversion, you should have the low pass filter. You should have. I have removed that. There's a possibility to run the low pass filter also on the PSOC, on the analog blocks, but I have removed that part from this exercise. It yeah, you can do it. You can do. If it's optional part. Let's make it optional. If you really want to do it, yes, you can. Yeah, I can show you the tricks how to do it, but anyways, usually you will have the this kind of the construction. So anti-aliasing filter, then sample and hold, and then A to D. Although sample and hold usually are one package, the A to D converter usually does it for you. Okay, and then basically, well, in our case, we have this optional, so this can be optional low pass filter. Okay, then you can also, since here we have something like 20 degrees Celsius, max 30 degrees, maybe up to 40 degrees in this room. So the maximum voltage of that one is about 800 millivolts. And your A to D converter voltage range is roughly 0 to 4 volts. You can put it like that. So you can actually get some. Where's my? There. You can actually get some extra resolution by putting the programmable gain amplifier here, analog block PGA. In any case, you might actually need it because this is the easiest way of routing the signal from different locations to the A to D converter. Or, well, you can, depending on the A to D converter, basically, you can also this PGA may be part of the A to D converter. Could be. All right. So after that, you will have the digital result at rate, quite high sampling rate. That's roughly, say, about 100 samples per second. Oops, samples per second. Yes. Okay. Depending on the again on what kind of A to D converter you choose. Your end product should have sample rate of 2 samples per second. So what you need to have here is a, I think the correct word is boxcar averager. So you will take the 0.5 seconds and just calculate the sum of values and also the number of values. And twice a second you just go, the output is basically just this sum divided by num. Okay, that's the way to do this downsampling in this case. Although if you have taken this digital signal processing class, you know that the this is same as it's quite bad low pass filter. You could do much better with, you know, by really filtering this data instead of just taking some. But I'm not recommending making digital filters there yet. That will be advanced stuff. Have you taken the what is that called? The DSP problem solving with MATLAB course last fall? Did you take? No, not yet. It will be next. Yeah, yeah. Hmm? Yeah, from Manfred Juncker. Yes, yes, but not the lab part. Okay. Okay. Yeah, next fall, week 42. I'll be here giving the DSP problem solving with MATLAB. But you would be in Vietnam at that time, or no? You will be here. Okay. Okay. Good. Excellent. So you can come to my class again. It's so cheap to you. And you will be also there if everything goes right. Okay. Good. Yeah. So that's the system, and well, that output then just is displayed on LCD. Okay, so let's see what parts we need. LM35. LM35. Here you go. If you are not familiar on handling this kind of electrostatically sensitive devices, you know that you take the those overcoat off, since that looks like it's yeah, take this one off, since it's you might get some you know, discharge. Yeah, and then when you pick a this kind of device by hand, make sure that you pick all of those legs at the same time. It doesn't guarantee that you wouldn't destroy it, but it helps. Okay, pick it from the that one, and also you have a kind of that kind of coat. There you go. Good. So that's the sensor. Let's take a closer look at the sensor. So, okay. Yeah. There's the link to datasheet of LM35, and that's it. Sorry, not 20 millivolts. It's 10 millivolts per centigrade. Where did I get that 20? So 10 millivolts per centigrade. So we have actually maximum about 400 millivolts. So we can actually here use gain of 10. Okay, good. And this is a TO92 package. And if you ever use this one in Finland, you should use the negative bias. And then the pin configuration. Okay, there. And observe TO92 package. This is bottom view, meaning like this. Bottom means that you're looking at the legs. Okay. So ground is now on my right hand side here. Yeah. Still on the right side. Good. Yeah. So that was the tricky part. Okay, the rest of that stuff actually goes into part that we need piece of designer. In this exercise, you would be using this some generic, not generic, but the miscellaneous digital devices like LCD. Again, that is for displaying the result, and our LCD is still on port 2. We also need a to D converter. Let's see. Yeah, let's take first the A to D converter. Okay, several different types available. There's incremental A to D converter, which is basically the single slope integrating A to D converter. Not really accurate, but it's simple. Another one. Then there's actually delta sigmas, 11-bit delta sigma and 8-bit delta sigma A to D converter. Dual ADC. I don't remember which. I think it was dual delta sigma A to D converter. Then there's easy A to D converter. That's also sigma delta. But that one is easy to use. If I was given a free hand which to use, I would use that easy A to D converter. Actually, then you can also select the what is your desired resolution versus what is the sample rate of this one. And yeah, this can be done self-running easily. Okay, then there's a successive approximation register type of A to D converter, only 6 bits. But SAR is basically quite fast converter compared to delta sigma, but it requires that sample hold. Okay, then we have this 3 A to D converters. So this was dual, this is just triple, yes. Not trial, but dual and trial. All right, so a 3-channel A to D converter, 2 kinds. Okay, let's click on the easy A to D converter, and then we can actually see if there is also the PGA, a possibility in front of that. If not, then we will add that one there. Okay, first thing, okay, we need to select the configuration. There are different configurations, single stage modulator or double stage modulator. Okay, I have no idea what is the real performance difference here. I don't think that there is much. It's just different configuration. At least that doesn't say. Second order modulator requires 2 switch capacitor blocks, one more than the first order modulator. Vertically. Well, we can use that one since it takes the vertically. When you look at these, so it takes 2 blocks instead of just 1. We are not going to use the much of the switch capacitor blocks in any case. So yeah, I think we can take this double stage modulator. Maybe. Oh, wow. That's nice. This is actually quite nice, since now we also can actually run the input signal from this multiplexer, but using this multiplexer, we have a problem. So the problem is that we cannot route this in the data from port 00, only odd pin numbers on that multiplexer. But we can always drag and drop this one here. Does it help? Yes, it did help, but it actually takes the output from this block. Or the input actually must be coming from that block. Wow. Let's try this way. Well, same thing. Okay, let's put it back there and then do some routing. So depending on where you actually put this one, dictates where you get this signal from. So input signal on these columns can come from any analog pin, but signal to these blocks can come only on the odd pins, right? Oh, wait a minute. Well, this would be also even. Let's see if it fits on the last one. Yes, it does. Excellent. Excellent. So now we can take actually the input from here. So placing these modules actually requires a little bit of checking how you get the signal routed to the system. Okay. So now we can basically start making the selecting the inputs either from here or from there. And there's the first one is the data format. Unsigned is okay. Unsigned integers. Resolution, well, resolution is then basically inversely proportional to the sample rate. Higher sample rate, less resolution. That's the sigma delta how it works. So it's basically sigma delta sample rate and resolution. So if you have sample rate and resolution, it goes like that. You know, that comes from the sigma. So that's the same as the first order low pass filter. Okay, good. And just a small reminder, this also takes some digital blocks because it basically requires also the sample clock rate. And the switch capacitor sections, they don't work unless you have a clock there. Okay, so now I need to take a look at the datasheet. I think this sample rate given here is kilo samples per second. So if you have a 14-bit resolution, it means that your sample rate here is 30 samples per second. Oh, okay. Well, that actually fits just fine for our purposes, almost, but on the exercise, I want to have a little bit higher sample rate. So let's see if we take that one to about 118. And then we need to take a look at the data sheet. Can we do that? Okay, we can get 11 bits. Don't try to use 14 bits, since I would guess that you are getting garbage out of the A to D converter. So try to match the data sheet sample rate versus the resolution table. Okay. No, it's okay. 108. Yeah. Yeah. Input. Not from reference low, but analog column input multiplexer. There. It comes. The signal comes from this multiplexer here, which is currently connected to port 00. That's excellent. All right. So we can actually also have this PGA, a programmable gain amplifier here, and run it at, for example, 8, with a gain of 8. Gain of 16, there's a chance that we are saturating the input of the HUD. Gain. We can actually put some extra gain. So it's, yeah, yes. Maybe. The reference. Okay. Reference here matters, since reference can, for the A to D converter, can be either here, which is the analog ground, or at the 0, which is the VSS. Using the analog ground actually would also affect on the gain. So our signal is somewhere here, and we want to multiply this one, not that difference. Selecting the reference to analog ground would actually multiply this difference by 8, meaning here. Okay, so we need to select the reference to VSS. All right, so analog ground output, disable offset compensation. Okay, what is the offset compensation? Let's see what it is all about. Parameters. For more details on correlated double sampling, refer to application note. Okay, we have the VSS as a reference, so we are not using the offset compensation. Yeah, but that has something to do with you getting a little bit better performance in some cases. Okay, so now we have more or less the easy HUD converter ready for doing the calculations. Then, of course, you need the timer to do the interrupts. Yesterday you already had a timer there. Was it 16-bit timer to give the about 2 second? Yeah, was it 2 seconds? No, half second. Yeah, interval timers. So timings is. I would guess you can do the same timer also in here, and parameterize the same way as yesterday. Okay. Now, timer 16. On the software side, you need to do this. That one. Okay. So, on software side, let's C. You need to start the modules, enable interrupts. Okay, and then you need to have the while one loop. Which checks if not conversion, but if it is time to display. If it does, then it displays. Or actually, then calculate the sum divided by num and display it. Okay, and that's all you need to do there. Well, maybe go to sleep. What else you need? You need interrupt service routines. So one for the timer. Yeah. So one for the timer, which gives you that so this is the actually sample rate, the FS timer. So it's this is our sampling timer for the output. Yeah, sampling rate timer. Good. And then okay, you need also you need actually also a routine for the ADC. Interrupt service routine for to calculate sum and increment num. All right, and of course this one is the for easy ADC. So easy ADC is a self-running, which means that it has its own interrupt service routines that take care of the stuff there. How? Let's take a quick look at easy ADC. Let's see. Yeah, in.asm. So same way as yesterday, interrupt service routines. Also, the easy ADC, all the interrupt code is on that assembly file. It has a little bit more code than earlier because, well, that's the engine for the A to D converter. So, yeah, I'm not really interested about that section. What I'm interested about is find a place where we have a conversion ready. Insert your custom code above. So I would guess, yes, sample data is now in iResult. So you can add your own code right here. So not long jump anymore. You cannot use long jump, but long call, since you still need to come back for that stuff. And basically, you also would like to. Okay. Interrupt service routine has already preserved the values of the A register. If you need to use the X register, you must preserve its value and restore it before to return to interrupt. We don't know if the C compiler is using also X register. So basically, on yesterday there was these couple of commands to restore and save the register values. Take a look at that code. So this is quite important that you still that the processor somewhat does what it's supposed to do even after calling your own own code. See, and this would be decimator. Okay, save that one. I close. Okay, that can be there, and basically here is your void function, which does the num plus plus sum plus equals whatever. Take a look at the API of this A2D converter, easy A2D ADC, to find out how do you read the value. Couple of comments. Remember that this num and sum are now accessed on both on the decimator and also on the main loop. So basically, you need to have these global variables. Num can run up to 180-ish. So character would be enough, right? Yeah. Initialize to 0. But then we have 11-bit A2D conversion. But we are calculating the sum. Yes, so basically we are summing up, and then after everything is done, then we divide it. And sum can actually add 7 more bits into that one in maximum. The worst case scenario is that we need 11 plus 7 bits. So we need at least 18 bits. So long int. Not int, but long int. 32-bit int. Floating point operations without the floating point accelerator coprocessor would take a few hundred clock cycles each. So it's better to use just integer as far as you can. You know, these floating numbers on microcontroller, 8-bit microcontrollers, those would be kind of waste of resources. But anyways, this one would be unsigned long int. Sum. Okay. Couple of notices. To make sure that you actually have the same type values on calculations, you need a lot of type casting in here. So cast it to same before adding, just to be on the safe side. The compiler should take care of that, but well, I don't trust the compiler. And this is basically a kind of standard way of doing stuff. Okay, then another thing, when you display the display routines, how to actually those work, that's another thing. Okay. Calculate sum and num and display raw value, and then calculate the temperature. So this one needs some scaling, calibration. So 1 degree Celsius is 10 millivolts. That's one scalar. Then we had the we had also the gain of 8 on easy A to D conversion. Then one we didn't actually check yet. Let me save that one and go here and look at the global resources. So basically, we haven't checked yet the reference multiplexer. And when we are running this 5 volt A to D 5 volt system, then we can use actually, I think 2 times band gap plus minus band gap. One band gap is 1.3 volts, I think. Was it 1.3? Need to check it from the internet. Let's ask internet. Band gap. What does it say about the band gap? Huh? What? Gap. Yeah. Band gap. Okay, better. What is band gap? Okay, maybe we can. Yeah, it tells about the diodes, and okay, there we have. Okay, it's about 1.3 volts. So I remember it just about correctly. So minimum, maximum, yeah, that actually typical piece of band gap performance. So specification says, well, it's 1.3. We can use the 1.3. So that one would be 2.6 volts plus minus. Wait a minute. No. Sorry. That's even better. So basically, the problem with that 2 times band gap is that we are missing the lowest values, and we need those lowest values. But 1.6 times band gap plus minus 1.6 times band gap. 1.6 times band gap is about 2 volts. roughly about 2 volts. And this one includes also the 0. So it's about 0 to 4 volts the range. Right. Am I correct or am I correct? 1.3 times 1.6. 2.08. Okay, it's about, yeah. So, yes. So another scaling factor here. Okay, generate the configuration files. So basically we have 11 bits max, or actually 0x, let's see, 1, 2, 3. Is it 7F is the same as 4. About 4.16 volts. Okay, so you need to do some conversions here. 11 bits and is equal to the highest value on A to D converter is the same as the 2 times band gap. Yes. No, 2 times. Yeah, the 2 times 1.6 times band gap. So it's the full range. Yeah. So that's 1.6 times a band gap. Yeah, that was 2.08. Yes, roughly, with some tolerance. Okay, so the first thing what you need to do is to get the A to D conversion results. So if I was you, I would probably just forget the interrupt ruts for a while and just get some results to the LCD. And that's the first task in any case. And see if that value actually makes sense, meaning that if you heat the sensor with your finger, you can see the increasing values. And when we cool it by a Finnish fingertips, then it goes down. Yeah. So yeah, that's the first task. The second task is to make this this decimator running. So have a hookup on the easy A to D conversion and have this one running, and then maybe display those once in a while debugging, and then basically the sampling timer. So 2 times a second it should give values which are somehow related to these. So calculate sum and num, display. Just for fun. Now we are talking about values which are volatile, meaning that they can disappear at any time. This one here is interrupt-driven routine. And basically when you are calculating the sum, how you can be sure that your sum and num are from the same round? The only way to make sure that this happens is that you stop ADC, then calculate sum divided by num, and after those are saved, then restart ADC. Otherwise, calculation does not necessarily give you what you want. And well, reinitialize those values. Since you need it only to calculate the sum between sum and the number of values during that half second time. Okay, so that's the whole thing. You just need to fill in the blanks. Good. Any questions? Not yet. Okay, if you get some, I will be here.